Good afternoon, everybody. Welcome to today's webinar on white box coverage metrics in automotive software testing. I'm Rex Black, president of RBCS. We are a worldwide testing quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, we've delivered insight and confidence to hundreds of clients around the world. Our team of international consultants deliver customized training, consulting, and expert services for companies that are looking to improve their test and quality assurance practices. I have over 35 years of software engineering experience, primarily in the areas of software testing, software test management, and software test automation, and am the author of 14 books on software testing. If you have any questions during the course of the webinar, please feel free to submit them throughout the presentation via your webinar interface, but please note they are answered only at the end. If you are listening to this webinar as a podcast, what I would encourage you to do is go to our website and download the slides, the PDF version of the slides, because there will be a few cases where I'm referring to some figures that what I'm saying is going to make a lot more sense if you're looking at the figures on the page. I hope you enjoyed this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS, we are a not just for profit company. Now that said, we do need to keep the lights on, especially given the kind of things that are going on lately. So if you feel that these webinars demonstrate a grasp of the kinds of testing challenges that you face, please give us a chance to bid on any and all software testing, consulting, training, and expert services work you might have. For example, we now offer the ISTQB Automotive Tester Certification, and if you're listening to this, you may very well be a potential customer for that. So, that said, no further ado, if I can just work my interface here. Whoops, how about that? Continue on to the next. All right, so this is a interesting statistic, I think. That's the code in a Ford F-150 truck, which is the most popular truck, is more than the code in a Boeing 787. So there's a lot of code in automobiles, and this truck is just one example of that. It's not limited to trucks. Any vehicle that you buy these days is going to have a lot of code in it. So there are standards for automotive software testing, and these include ISO 26262, Automotive Spice, and AutoSAR. Now, some of these standards set levels of code coverage based on the level of safety risk, called the ASIL, which we'll talk more about. And these levels of coverage include statement coverage, decision coverage, and modified condition decision coverage, or MCDC. And so in this presentation, I'm going to explain to you how to understand those three important coverage metrics and how to understand what the tools might be telling you if you're using a tool to achieve compliance. All right, so we'll start with it's kind of an overview of control flow coverage. So there is statement coverage, which is also called instruction coverage or code coverage, which refers to every statement being executed at least once, every executable statement. And then there's decision, which is sometimes referred to as synonymously with branch coverage, and I'll explain why that's not quite right. But this is where every possible decision outcome has been at least once true and at least once false. Now, then there is condition coverage. Now, condition coverage and decision condition coverage are not very interesting by themselves, but they are building blocks to get us to MCDC, or modified condition decision coverage, which is interesting. So condition coverage says that every atomic condition has to be evaluated at least once true and at least once false. And decision condition coverage says that we have to achieve both decision and condition coverage. Now, modified condition decision coverage, or MCDC, says that each condition alone has to be able to force the outcome to be once true and once false. In other words, if that condition had taken on the wrong value, the outcome, the decision outcome, would be reversed. And I'll explain why that's important when we get there. Now, there's another form of control flow coverage that's referred to as multiple condition coverage, which is all possible combinations of conditions in a decision. And when we get there, I will explain why you should not do this. All right, so here's a really simple example. I have a chunk of code here that calculates a factorial using a loop. Some of you may be familiar with doing this with recursion, but I'm using a loop. So if we reconstruct that as a control flow diagram, you see that's on the right. The bubble at the top is lines 4, 5, and 6. And then there's the if statement is there in the subsequent bubble, and that introduces a branch. It's a decision point. And if we do the true side, we do lines 8 and 9. And then we would go and exit through the return. That's line 17. If we do the false branch, the false decision on line 7, we then go to line 10 and fall through to 11. And then we go to line 12. And depending on what the input was, we will iterate the loop body 0 or more times. That would get us through to line 13. And then after iterating the loop or not, we would then print our factorial value, and then we would exit through line 17, the return. Okay, so pretty straightforward piece of code there. So if we want to achieve 100% statement coverage, in other words, every statement has been executed at least once, then what we would do is we would take a negative value, so say -5, and we input that at line 6, which is where it accepts an input. And then so if -5 is less than 0, that will result in a true decision at line 7. So then it will take that red path, and it will print the error message and say invalid -5. And then it will set the return code to -1, because that's the code that this program uses to say, I got an invalid input. And then it goes to line 17 and it exits. And then if I use, say, 5, so as the input next, I go line, I'm going to input n equals 5. So do lines 4, 5, at line 6, I input 5. So if 5 less than 0 evaluates to false, so it then does the else branch, goes to line 10, to line 11, it initializes the factorial value, and then it is going to count up the factorial, so all the way up to 5 factorial, which, if I remember correctly, is 120. And then it will, so after iterating the loop 5 times, it will go to line 15, and it will print out 5 factorial equals 120, and then it will exit out of line 17. Okay? So notice that every statement, every executable statement there has been executed at least once, right? And that's what you need for 100% statement coverage. To the extent that you've not executed each line, what you do to calculate statement coverage, you take the number of statements actually executed and divide it by the total number of executable statements. Now, let's talk about a decision. So computers are more than just calculators. They have the ability to decide to do one thing or the other. So the decisions are typically going to be driven by Boolean expressions. Now, in the case of a switch case construct, that's a little more complicated, because what you have is this implied value equals constant expression that's not actually stated in the program, but it's implied by what the switch case construct is doing. Generally speaking, you're going to have some sort of explicit or implicit Boolean expression, and it could be a simple one like shown here, a greater than b, so that's one value greater than another. So I've got a value, could be a constant, could be a variable. I got a relational operator, and I've got another value, again, a variable or a constant, right? Now, in some cases, the expressions are more complicated, as we see below. So we've got a greater than b, or x plus y equals -1, and d not equal true, which is that last expression there is really quite tortured, and one should not do that, but sometimes you see these kinds of things. So there are various programming language constructs that provide for decisions. So we see the if then else. Sometimes it's just if without an explicit then, like in C. There's the while, so that's a loop, but a loop is also going to be based on decisions. That's the branch at the top. There's the until do, or repeat until, which is the branch at the bottom. You got the for loop. You've got the switch case. So there's a lot of these available. But the basic idea is, at a decision point, the program does one thing or it does something else. So 100% decision coverage would mean that every decision outcome had been at least once true and at least once false. So going back to statement coverage, let's think about this. So we tested with -5. So we went down to if -5 less than 0 at line 7, right? So that would say, okay, I now did the true branch there. So the true outcome is covered. And then I skip lines 10 through 16, which includes the decision at line 12. So I've done 1 out of the 4 decisions in the first test, -5. So my decision coverage at that point is 25%. Now, when I put n equals 5 in, that's the next test, then I do the false decision at line 7. So now my decision coverage is up to 50%. And then I go down to line 12, and I go right at this I less than or equal to n. That's going to be true, 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 false, right? Because it's basically counting up to 5, right? So it did true at least once, and it did false at least once. So now I've got 100% decision coverage. Okay. Now, you might not like that, because you might say, well, I think, shouldn't we also have a test where we don't do the body of the loop? Shouldn't that also be something that we do? And there's a name for that. That's branch coverage. So if you're familiar with McCabe's cyclomatic complexity and basis path testing, that's what you would be doing there. You'd be covering those branches, because that is in McCabe's concept a independent branch. Okay, so that's something to keep in mind. Depending on the tool that you're using, it might be giving you decision coverage, it might be giving you branch coverage, it might be giving you decision coverage and calling it branch coverage, or vice versa. So you need to check that, because what I've found working with clients is that the tools use different nomenclature for these things. Okay, so statement coverage and decision coverage will be two levels of code coverage that might be required based on the ASIL, the safety risk associated with the particular piece of functionality. So it could be just statement coverage, or it could be statement and decision. But here's a hint: if you get 100% decision coverage, you're guaranteed to get 100% statement coverage. It's not the other way around, though. It did work that way in the example that we just looked at, but that's not always true. Okay, but it might be that you need to get MCDC coverage, modified condition decision coverage. So how do we do that? Well, we have to start step by step and go through the building blocks here. So we need to look at something called condition testing. So decision testing looks at the overall outcome of the Boolean expression. Condition testing is looking at the atomic conditions within the Boolean expression. And the Boolean expression may have 1, 2, 3, 4, however many atomic conditions within it. Now, in condition testing, all we require is that each atomic condition has to be at least once true and at least once false. Now, again, this is not something that you're likely to use, not directly, because it's mostly something that's going to be useful as a way of understanding MCDC. However, it is useful to be aware of what condition testing is, because I came across a situation with a client who was using a tool that was reporting statement coverage, and it was also just reporting condition coverage. And at first I thought, well, surely the tool maker has confused condition coverage and decision coverage, because decision coverage is useful by itself and condition coverage is not. But it turned out that actually the tool was reporting condition coverage. And as you'll see in a minute, this can be a little dangerous, because it's possible to get to 100% condition coverage without getting to 100% decision coverage. Okay, so if you're dealing with decisions where the Boolean expression is a single atomic condition, you will always get decision coverage out of condition coverage. But if it's a compound Boolean expression where there's two or more atomic conditions, it may not. So I think I've got an example for you. It's not in this slide, but it's coming up soon. So first, let's explain atomic conditions. So atomic condition is, the word atomic, of course, means that it's indivisible, right? Can't be split into a smaller piece. Of course, we started calling things atoms, and then we found out, whoops, those actually can be split into smaller things. At least this is, chemistry and physics. But atomic in its, meaning in programming is it cannot be divided. So basically, an atomic condition is something which cannot be broken down into constituent pieces and still result in a true-false outcome. So an atomic condition can be a single variable or value that can take on a true or false outcome, like the X that you see there, which in this example is true, or it could be false. We can also have two atomic conditions, so D and F. The two ampersands is the relational operator, typical relational operator. Excuse me, not relational operator, Boolean operator, that joins D and F together. So D is an atomic condition that takes on a true or false value, and F is an atomic condition that takes on a true or false value. So if we have true and true, then we would have, the outcome would be true. But if it's false and true, true and false, or false and false, the outcome would be false, as shown in the example here. And we can have a situation where we have three atomic conditions, like A or B, and that's in parentheses to force precedence of evaluation. And then we say, and C equals D. Now, or is a Boolean operator, but the equals there is a relational operator. So the C equals D cannot be split, because if we split those, that's no longer something that produces a true-false value based on the quality relationship. And then we have the tortured example from one of the earlier slides there, A greater than B, or X plus Y equals -1, and D not equal true. So that's don't write code like that, but that has three atomic conditions. But notice, as it says, there's only one decision, right? The decision is the ultimate evaluation. The atomic conditions each take on a true-false value. So in condition testing, as I said, we would make sure that the conditions were once true and once false. So the previous slide, then you would test, the Boolean variables X, D, F, A, and B all be once true and once false, and then the relational expression C equal to D would have to be once true and once false. The relational expression A greater than B, once true, once false. The relational expression X plus Y equals -1 would have to be once true and once false. And then the relational expression D not true would have to be once true and once false. So that's condition coverage. And now decision condition testing is where you require 100% condition coverage and 100% decision coverage, those two things. Now, in the case of a simple Boolean expression like A greater than B, that's going to be the same. So it's going to be true, false. So the condition coverage is achieved, true, false for that atomic condition, and the decision coverage is achieved because the overall decision was true and false, right? But whoops, for this guy here, notice that I've got A greater than B, X plus Y equals -1, and D is not equal to true. Okay, so I could go A greater than B true, X plus Y equals -1 true, and D would be false, so it's not equal to true, so that's true. So true, 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 okay? And then I could have A less than or equal to B and X plus 1, some value other than -1, and D is equal to true, so that's false, so this would be false, false, false. Now in that case, I would have gotten 2 tests, and each of the atomic conditions would have been true and false at least once, and the decision would have been both true and false at least once. So that would have gotten me both decision condition coverage. But check out this. What if I did A greater than B true, and then X plus Y equal -1 false, D is equal to true, so that's false. Okay, so it was true, false, false. So the decision there would be, well, wait a minute, sorry, let me back this up. Let's say that A greater than B is true, and X plus Y equal -1 is false, and D not equal to true is false. Okay, so I've got false, true, false. Well, the overall outcome is going to be false, and then I do it so, or excuse me, true, false, true. So the overall outcome is true, and then I do false, true, false. Nah, that's sorry, I screwed that up again. Let me back that up one more time. So if I can have a situation where the expression evaluates to false both times, even though all of the our atomic conditions have been once true and once false. Let me try to explain that with a simpler example here. That one's complicated, and I keep getting tripped up on it. So take a look at this guy. If A and B, okay. Now notice that if I test A false, B true, and A true, B false, the outcome is false and false both times. All right, see that? So notice that I got condition coverage, but I didn't get decision coverage. Now, if I add another test and say A true, B true, then the result will be true. Now, that would be 3 tests. Now, I could also have just tested A true, B true, which would be true, and A false, B false, which would be false. And true is true, false and false is false. So I could get it in 2 tests. But notice that if all my tool does is look at condition coverage, then what I'm going to get is not necessarily 100% decision coverage. Okay, hopefully that example made sense. Sorry it was so difficult for me to work out in my head the solution to that, but there is a way of coming up with a test for this expression here, the arbitrarily complex one that will achieve condition coverage and not achieve decision coverage. And when some clever listener wants to put that up in the question Q&A, I'll read it out and congratulate them for being able to do what I was not able to do. The problem was I can't do it on paper right now, and if I were able to write, then I would do it, but trying to do it in my head was too complicated. Excuse me. And no, that's not a COVID cough, just a throat clearing, talking and dry throat cough. Okay, so MC/DC coverage says it's modified decision condition or modified condition decision coverage. It's a condition decision meaning the same thing. So we're going to make sure that every condition's been evaluated at least once true and once false. That's the condition part. The decision part is that the outcome has to be at least once true and at least once false. But then it adds a third thing that has to be true about the set of tests. Each atomic condition has to control the decision outcome once true and once false. And again, what that means is that if any atomic condition were to switch from true to false or vice versa, that would switch the decision outcome. And the reason that that's important is the switching of the decision outcome is the thing that you can catch in a dynamic test, right? Because I can see that it took the wrong path in the code, that it did the false side when I should have done the true side, or it did the true side when it should have done the false side. But what's typically not an externally observable behavior is the value of the atomic conditions. See that? When you're running the code, unless you're actually stepping through the code in the debugger, you're not going to be able to evaluate or see the values of the atomic conditions. So what I need is a test technique that makes the values of the atomic conditions visible to me in the most efficient possible way. And that's what MC/DC is going to do for you. It's going to create a situation where if any atomic condition has taken on the wrong value due to some sort of defect in the code, you will see that because it will go down the wrong path. Now, the nice thing about this is it's efficient because if you have n atomic conditions, it will typically only require n+1 tests. So it scales linearly with the number of atomic conditions, which is not true of multiple condition coverage. And we're going to see a little bit later why we don't want to use multiple condition coverage, because multiple condition coverage will tell you the same thing. It'll basically force the exposure of the value of the atomic conditions in externally observable behaviors. But the problem is you're going to pay a really high price with it from a testing point of view. Now, this is the level of coverage, MC/DC. This is the level of coverage you're going to have to get to when you're dealing with the most safety critical portions that have the highest ASIL or automotive safety integrity level requirements. Now, there can be some situations where coupling of conditions, so this is where you have, say, shared variables in two or more atomic conditions, or situations where the value of one atomic condition is such that it makes the one possible value of the other atomic condition nonsensical. Also, compiler short circuiting can affect this, but you know, that's something that's beyond the scope of what we're going to talk about here. You come into these situations, you'll have to just figure out what the right thing to do is. Now, MC/DC is, as I said, it's nice, efficient way of getting a very high degree of risk mitigation, but it's one of those things that if you were to try to work it out in your head, you would be even more tripped up than I just was a few minutes ago when I tried to work out in my head that illustrating condition coverage versus decision coverage on that arbitrarily complex expression. See, I did that on purpose. I wanted to show you, you know, you try to work that out in your head, you're just looking at that. That's just decision condition coverage, right? It's really complicated. And you add this third piece of, oh yeah, and by the way, every atomic condition has to be able to control the outcome at least once true and once false. Well, that's going to be even harder to do in your head. Fortunately, there is a systematic process for doing this. Now, it cannot be done in your head, but it can be done on a piece of paper or on a computer or, excuse me, on a whiteboard. So here's what you do. Let's say that we're dealing with the expression A or B. So A is one atomic condition, B is the other. Okay, we have two atomic conditions, A, B, and they're joined together with an OR operator. If you're a C person, think, you know, two parallel bars here, right? So A or B, and notice that A or B can evaluate to true or false. This is true of any Boolean expression, no matter how complex it is. It always evaluates to only true or false. So we write this table, and the table has 3 columns. The first has the logical expression or Boolean expression. The second column is the true column for the tests that have a true outcome. And the third column is the false column, which is the tests that have the false outcome. Okay, so that's step 1. And then what we want to do is add a blank row for each condition where the number of blanks is equal to the total number of conditions. So you notice that at the upper right-hand side, the very top, we have the 3 columns, right? And then we have 2 rows below that. We have the A row and we have the B row. And on the A row, there are 2 blanks under the true column. The first blank corresponding to the value A is going to take on, and the second blank corresponding to the value that B is going to take on. And then the same thing is true in F. There are 2 blanks in the A row under F, the first corresponding to the value that A is going to take on, and the second corresponding to the value that B is going to take on. And then in the B row, we have exactly the same thing, B, okay? And then we have the 2 blanks, first blank A, second blank B for true, and 2 blanks, first blank A, second blank B for false, okay? And the A row is the set of tests where the A atomic condition is the thing that's forcing the value to be either true or false. And the B row is the set of tests where the B value is the atomic condition forcing the outcome to be true or false. Okay, so the top part of that table, the top quarter of that table, if you think of that table being divided into 4 equal-sized quarters, right? And that's what it actually is. You should think of them as 4 separate tables, right? So that top table is what you have at the end of steps 1 and 2. Now, the next step, number 3, what we're going to do is we're going to fill in the diagonal blanks in the second column with T, okay, and the third column with F. Okay, so that is A is going to take on a true value, and that's in the A row, right? A is going to take on a true value, and A is going to take on a false value. True in the true column, false in the false column. And then in the B row, B is going to take on a true value, and F is going to take on a false value. Or B is going to take, excuse me, B is going to take on a true value, and B is going to take on a false value. Okay? So that's the end of step 3. Okay? Now remember, in the A row, the A is supposed to control the outcome. So A is going to force the outcome to be true and false. And in the B row, B is going to force the outcome to be true and false. So what we need to do is use what are called neutral values to fill in the other blanks. So the third table there, what we see is putting in neutral values. So with an OR operator like we see here, the neutral value is false, because false or false is false, false or true is true. So you see how false is the neutral value there? It doesn't control the outcome. See that? So what we're doing by filling in the remaining blanks with neutral values, we're putting values in there that don't control the outcome. That's how A and B, depending on whether we're talking about the A row or the B row, get to force the outcome to be true or false. Now, if we were dealing with an AND, it would be exactly the opposite. The neutral value is a true, right? True and false is false, true and true is true. Make sense? Now, once you have done that, what you will typically find is that there are duplicate tests. So we have false and false in the false column of the A row, and we have false and false in the false column of the B row. So we don't have to run them twice. You're typically going to find that. Okay? Now, you might say, well, doesn't that undermine this controlling value idea? Well, how could it? Because if the same exact test is in two separate cells, I mean, obviously the test doesn't behave differently depending on which of the two cells you select it from. It's just false, false, right? In this case, false or false, right? So now if you think about it, notice that in the A, let's look at the A row at the bottom table, okay? So if in the true column, if the A value there, which is now true, becomes false, notice that we now go from true or false, which is a true outcome, to false or false, which is a false outcome. It flips the decision. Similarly, in the A row, if we take A and change it from false to true, then we'd be true or false, and it would go to true. So that would flip the decision. Now look at the B row. If in the B row, if B takes on a false value instead of a true value, the outcome will be false. And similarly, with the B row, we look up above in the A row because it's the same test. If B takes on the value true instead of the value false, the outcome will flip to true. And we'll be able to see that when we run our tests. Make sense? All right. So let's get a little bit more complicated here. Let's say, what if we have an A or B quantity and C? Now, decision condition coverage, notice if we just say A true, B true, C true, A false, B false, C false, that's decision coverage, yes, been true and false once. Condition coverage, yes, A, B, and C have each been true once and false once. But notice that B never independently affects the outcome. So in the first row there, A true, B true, C true, if I flip B to false, well, true or false is still true. See that? So true and true is true, so the outcome remains true. And in the second row, A false, B false, C false, if I flip B to be true, well, false or true, now that's true, so the A or B is now true, but true and false is still false. So notice that in that case, we could have a situation where the value of the Boolean, the atomic condition B, was taking on the exact opposite value of what we expected. And those tests, those two tests that got decision condition coverage, would not catch that. And that could be bad, because there certainly could arise situations, probably will arise situations, where the value of B does actually independently affect the outcome of the decision. And if it's taken on the wrong value, any number of things could happen, like, oh, say the cruise control doesn't disengage. Think, Toyota stuck accelerator situation. I get that there's controversy over whether that was a code bug or not, but, these are the kinds of things that could occur. Okay, so let's look at an example of MCDC with this more complicated expression. So we draw the three columns as described before. In this case, we have three rows, A, B, and C, and we have three blanks in each column. See that? So we got the true column and the false column. And then we put the diagonals, true, 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 false, false, false. So in other words, if you look at the second table there, A takes on true in the true column, and it takes on false in the false column. B takes on true in the true column, and it takes on false in the false column. And C takes on true in the true column and false in the false column. And then what we do is we replace the remaining blanks with neutrals. Okay, so false for or, true for and. Now, this is where things get a little bit tricky, okay, because we have this compound expression. So let's take a look at the first row in the third table there, the A row. So notice that we have true, A is going to be true, we know that. And then we got to pick a neutral value for or, so that's false. and a neutral value for and, so that's true, right? So true, false, true. And then false, false, true, right? Same neutral values there. And with B, the situation is the other way around because B has to be true. We need to pick the neutral value for A, so that's false. So in the B row, it's false, true. We still have to pick true as the neutral value for the and, right? And then the B row in the false column, B takes on the false value, so it's false, neutral value for A, false, true, true being the neutral value for and. But take a look at row C. Now row C, the C row in the true column, C has to be true, but what do the values of A and B have to take on? Well, we actually don't care what the specific values of A versus B are, as long as A or B evaluates to true. So what I did here was I put true, false, true. I could have put false, true, or true, true, but by putting true, false, true, I create a situation where notice that I have the same test in the true column in the A row and the C row, which is going to allow me to collapse those two tests, deleting duplicates, right? Unfortunately, that same trick is not going to allow me to do anything clever with the C row and the false column. I did true, false, false there. I could have done false, true. I could have done false, false. It wouldn't have affected it. But what happens when we get into the fifth step and we delete the duplicates is that what we see is that in the B row, in the false column, we've got false, false, true, just like in the A row, so we can delete that. And as I said, I carefully constructed the C row in the true column to be duplicative of the A row in the true column, so we can delete that. So I have 1, 2, 3, 4 tests. I had 3 atomic conditions, so 3 plus 1 is 4, n plus 1, right? Now, so if you didn't get that, if you didn't construct the conditions carefully with these compound expressions, what can sometimes happen is that you find that instead of having n plus 1 tests, you've got n plus 2 tests or n plus 3 tests. In that case, you would just go back and, tweak the places where you have freedom that's created by the non-controlling variables, non-controlling conditions. Are there other permutations of the non-controlling conditions that can be arranged in such a way that it's duplicative of some other test? All right. Wow. Okay, that's great. Huh? A little complicated. Might have to go back and think about that. I'd recommend that you download the slides and work through those as exercises to make sure you're clear on this stuff, because listening to somebody explain this without actually doing it by yourself, listening to somebody explain it will give you a sort of a basic understanding, but the ability to do it is something that requires doing it. Just like you can't have somebody, you can't listen to somebody talk about how to play a piano or do a YouTube video where they're describing how they're playing a piano and then sit down and play the piano. Okay, sorry about the ringing phone in the background there. This time I promise that wasn't actually an on-purpose mistake. Multiple condition coverage, let's talk about that. So what if you say, well, that MCDC stuff, that's really complicated, and rather than try to figure out how to do that, I'm going to just use brute force solution. The brute force solution is I'm going to exhaustively test every single combination of conditions, at least that could affect the outcome, and then take advantage of short circuiting and coupling and so forth, and not necessarily run all those, but I'm going to run every possible combination. Well, what you would do is you would generate a Boolean truth table, which would have 2 to the n entries in it. And then you could go through and you could collapse out some of those things that are, impossible because of short circuiting and so forth. Now, here's the thing, is that this is not a required level of coverage in automotive testing or in any other safety critical testing that I'm aware of. because it tends to be really expensive without giving you any additional risk mitigation. Now, what do I mean by really expensive? Well, you might remember the movie Fight Club. The first rule of Fight Club is never talk about Fight Club. Well, and one of the first rules of testing is never talk about testing everything. In other words, remember the principle of the impossibility of exhaustive testing, right? Which is connected to the other principle, another principle of testing, which is that testing can prove the presence of defects but can't prove their absence. So here's what happens when you try to test everything in terms of conditions is as the number of conditions goes up to, in this example, 8, the number of tests goes over 250. Ouch. So this may seem feasible, at some low level, like, if I say, well, we got 3 atomic conditions and 2 to the third is 8, 3 plus 1 is 4. It's half the many tests, and the picture gets worse and worse. So don't try to test everything. Now, are there bugs that you couldn't find that with MCDC that you might find with multiple condition coverage? Nobody has ever been able to show me an example of such a bug. Now, it is true that there are bugs that are very immune to structured white box or black box test design techniques. And there is an interesting write-up of one such bug by a guy named Doug Hoffman. Now, some of you may remember way back in dinosaur days, which was, I was 10 plus years in software engineering at that point. There was this CPU brought out by Intel called the Pentium, and the Pentium had a bug in its microcode that did division. And Doug Hoffman's did a write-up of that showed how difficult it would have been to find that bug through any approach other than exhaustive testing or extensive random testing. So it's not the case that, hey, we did MCDC and so therefore there's no way we missed any bugs. But it is the case that, at least as far as I know, and I've challenged hundreds of people around the world on this, that there's no instance that anybody's been able to cite to me where multiple condition coverage would have found a bug that modified condition decision coverage would not have found. All right, so there you go. Those are the 3 code coverage levels that you need to achieve for automotive testing. Statement coverage, which might be called instruction coverage or code coverage by your tool. Decision coverage, which might be called branch coverage by your tool. And if so, you need to make sure that, which one actually is it. And then modified condition decision coverage, which is unlikely to be called anything other than MCDC or modified condition decision coverage. I've never heard of that. So know which level of coverage is required. This is based on the automotive safety integrity level. That's we determined by applying the technique specified in the standard that you're following. If you are a tester, if you are an SDET, if you are a developer, you do need to know how to apply these techniques. And you might be tempted to say, well, just let the tool figure it out for me. But in the case of MCDC, you're going to need to actually construct the tests in advance. So that table that I showed you is something that you really are going to want to master. So as I said, download the slides and work through those examples on your own. And I think by the time you've done that, you'll feel more confident. If you take maybe a couple snippets of code out of your actual programs and apply it there, you'll be even more confident. All right, so I will put up the advertisement as we go to Q&A. So I will, shoot, put up the Q&A panel. Pardon me while I have to look over here. Yeah, it's dealing with some screen real estate issues, but all right. So let's see. Before we get into the questions, again, just mention, we love doing these free webinars for you all, but we do need to keep the lights on. So if you are in the business of doing automotive software testing, I'd really appreciate it if you'd consider signing up for that course. We've got it running, like all of our courses, of course, virtually now. So happy to have you do that. And of course, we are also doing our consulting and expert services virtually too. So if you need some help, let us know. And a couple questions here via email. Do the tools always give the right answers in terms of coverage? Well, unfortunately, the answer is no. They don't always give the right answers. I've had a situation, for example, with Debian Linux. Sorry, I got another ringing bell here. Push the do not disturb so that doesn't happen anymore. So with Debian Linux's built-in code coverage tool, we had a situation. I was teaching a course for some SDETs, and in a situation where the tool was saying that we were getting 100% decision coverage, but less than 100% statement coverage. And it was flagging some things, if I remember correctly, as executable statements that actually were not executable statements. And besides, they were, if you did think of them as executable statements, they were on paths that would have been executed anyway. So it was really weird. I didn't spend time trying to get to the bottom of it because I was teaching a course for a bunch of SDETs from LG, I think, or Samsung. It was a very long, intensive 3-week-long SDET training course that we put them through. So, rather than debug Debian Linux's code coverage tool, it was just like, well, that's clearly wrong. So, I'd say beware of that, and also beware of the using the wrong name for the level of coverage that's being measured issue, because that happens too. As I said, there's that example I just talked about where it's condition, it's calling it decision coverage, and it was actually condition coverage. And I've seen examples where it was calling it condition coverage and it was condition coverage, and that was weird. So just kind of be careful of that. Can you recommend any tools for measuring code coverage? That's the other question here coming through. I have made it a long-standing rule throughout my consulting career to not do this without actually not anything other than a consulting engagement for a client. And here's why. The best tool for your organization is going to depend on a number of factors. You have a number of requirements and constraints that affect your choice of tool. And I don't know what those requirements and constraints are. So if I just rattle off the names of tools, that doesn't do you a lot of good. In fact, that points you potentially in the wrong direction. What you need to do is follow the best practices for tool selection, which starts with identifying your requirements and constraints and risks and so forth. There's a really good write-up of the tool selection process in the ISTQB Advanced Test Manager syllabus, which I've expanded on in my book, which is Advanced Software Testing Volume 2, if I remember right. So I would say, follow a careful process. And all too often we run into clients that have made tool decisions and, without carefully thinking through their real needs. All right, so I just want to, I have to mention something. Somebody was asking a question earlier about signing up for the webinar with the intriguing email name, which I thought was ale sauce. like ale sauce. It's something you would make with heavy beer for a steak or something. But now I see it was ale sauce. So, so for one of our attendees, who is Catalina Alejandra Saucido. So, very, very clever email name. I hope you will forgive me for outing you. I guess you go by Ali. So that's quite, as I said, quite a clever email name. Okay, so seeing no further questions, just a little bit more about the resources available here, and then we'll head out the door. We run these free webinar sessions once a month, as you know, so sign up. We are mixing it up this year. It's not just me, it's me and other people, and more conversations and other points of view and other presenters and so forth. So we're trying something new. Let us know how you like it. You know, for years it was just always just me doing my thing, and now it's me talking to other people, and as well as me doing my thing sometimes. So send us some feedback. If you would like a special webinar presentation for your company only of this webinar or any other topic related to software testing, send an email to info@rbcs-us.com. Sign up for our newsletter at rbcs-us.com, and this will get you valuable discounts on consulting and training services, and well as a regular newsletter that keeps you posted on what goings on are. You see the Twitter, Facebook, and LinkedIn coordinates below. If you want to connect to me on LinkedIn, I will accept anyone who attends a webinar for sure. Just don't immediately start spamming me with all sorts of weird propositions that may or may not be of interest. This happens sometimes. I get somebody sends me a LinkedIn contact request, and the next thing I know, they're like, hey, you know, it's 3-paragraph long thing about, I'm going to come in and look at your sales and figure out how to make you sell 100% more than you currently do. And, you know, like, dude, I have been at this 26 years. If there were a magic bullet for doubling my sales on a whim, I'd already know about it. So I'm pretty sure you don't have it. So, you know, don't connect to do things like that. But I doubt any of you all are going to do that. If you know anybody who missed this webinar or you'd like to listen to it again, of course, it gets posted on our YouTube channel. You see down there, it's also posted as a podcast. This one might be a little challenging from a podcast point of view, though. If you're going to do it as a podcast, or you know somebody else who wants to do it as a podcast, just tell them, make sure you download the slides so that you can look at the code snippets as you're going. So finally, we offer these resources as a service to the software testing community because at RBCS, we are not just a for-profit company. But that said, we do need to keep the lights on. As you are all aware, these are challenging times. So if you feel that these webinars demonstrate a grasp of the kinds of software testing challenges you face, please give us a chance to bid on any and all software testing, consulting, training, and expert services work that you may have. This concludes the webinar. Thanks for joining us today. Look forward to seeing you in future webinars.